There is something that drives us every day to make things better. It brings cities to life and moves us every day. Something that boosts manufacturing and secures a robust power supply. It's something that creates lasting value for society. Something we call ingenuity for life.
Thank you. Welcome, everybody. It's very good to see a full crowd and to see all the family and friends of these students that have come here tonight. Just let me tell you a little bit something about ourselves before we tell you something about Siemens. Who are we? My name is Mieke Heggerus. I'm one of the Siemens sponsors. I'm the manager sales and marketing for the mobility division. I used to be in the team. So I'm also a very proud alumnus. I used to be a driver, and these days I'm also the commentating team in FS Germany, for the Student Germany event. And next to me, I have Stef, also a former member. He's my bid manager. He's responsible for fairly big projects, everything between 5 and 100 million euro projects. So quite some responsibility. He used to be the team captain of the 09 team. He's, let's say, a skilled presentator, and also one of the, I'm trying to put the bar a little bit higher, and also part of the commentating team in Germany. We are here today, let's see if at the airborne facility, but this used to be a military airfield, as you might know, and I'm sure some of the older audience knows this. It used to be an airport, and now it's a field lab, a technology center, a meeting center where we show our clients and customers and partners our technologies, and we have meetings here to think about the future and to discuss all the matters that are important for us. Just trying to find the button. Siemens at a glance, what do we do? Within Siemens, we dedicate ourselves to creating a better future. We have the motto, ingenuity for life, which means that we want to create a better future for our children, for our grandchildren, for the world. That means that we are involved in wind power projects. We have the Gemini projects out at sea. We are busy with, that's our wind power division. We have the energy management division, which is involved in energy management solutions and also smart grids. We have our healthcare division. They make MRI scanners and tools for healthcare. We have the power generation division. Think about power generation all over the world, big plants and so on. We have our process industries and drives. They build, for example, experimental electric airplane. And also we have digital factory division. And you might know them because they built the software for the Formula 1 teams, the winning ones as well. Last but not least, we have building technology. And they build sustainable CO2 neutral buildings.
The world today is always in motion, creating challenges that inspire our actions. We are courageous pioneers. We electrify, automate, and digitalize mobility. We work with boundless passion, constantly innovating and creating a new quality of transportation. We are taking mobility to the next level by making it even more efficient and sustainable. We manage the increasing needs to transport more and more people and goods. We always deliver what we promise. We raise the availability of infrastructure, fleets, and services. We take mobility further by providing digital solutions to improve passenger experience, and by developing the most advanced data services to maximize throughput. We make real what matters. We are the Siemens Mobility Division, and we take mobility further, together.
So thank you, Mickey, for the short introduction about the Siemens company. One division that was not on the previous slide, but we had a movie about this, is the Mobility Division. This is the division where Mickey and me, as Mickey told us, both work. And this is also the division that sponsors the racing team. This is, by the way, not really a coincidence. The question is, why do we sponsor these guys? That is, in fact, because the projects that we do in the Netherlands are, well, very much similar to the project that is Formula Student. And we wanted to talk also a little bit, especially also for friends, family, and parents, about the why it is so much similar, and what did we get out of this by being involved in the team. The projects that we do in the Netherlands are, we do them actually quite on our own. Siemens, of course, being a giant German multinational. The projects we do from A to Z, from scratch until service, by ourselves in the Netherlands, which is quite unique that we do that. You see large waterworks, both inland as well as, of course, the storm flood surges, the barriers that will be closed also tonight because of the high water, which you have heard probably in the news. Storms are expected, so we need to defend ourselves, defend our country. The systems that are in place on these kind of objects cannot fail. If they fail, well, where we stand now will be underwater probably. What we also do is tunnel infrastructure. You might not know this, but an average tunnel where you drive through has about 80 to 100 different systems in it in place to keep everybody safe. We all know, of course, the big accidents that used to happen in the past in the Alps. Since then, European law dictates that well, a tunnel should have a minimum of certain systems. We as Siemens provide turnkey solutions for those kind of safety critical objects. To the left below you see the control center, the command and control center, which we have in Limburg in the nautical center of Maasbracht, which governs the entire lower part of the Rhine River, including several locks over there for the water traffic. And to the right below, from our rail section from the mobility division, we also deliver rolling stock, both trams and trains, as well as electrification and communication infrastructure for rail applications. To the right below you see the trams in The Hague, for those who have seen it. So what did we get out of it? We tried to, well, see what did we get out of it and why are we sponsoring? We're sponsoring because, well, we are quite passionate about top performing teams. We want this also in our company. And hence, we would like everybody from the team to come and work at Siemens. Because the experience that you have gained is immensely valuable for businesses, not only Siemens, but for all business in the Netherlands and outside. If you are more interested about Siemens and about the mobility division where we work, please, you can visit the website below to see a little bit more information over there. And to conclude, we wanted to summarize a little bit what are, well, the similarities and the differences between the team and the work that we do on a daily basis in these kind of big projects. So I'll start with the similarities. Some bullets, we try to limit it a little bit because the list was initially a lot longer. We have teamwork in a very challenging project. But the emphasis here is on teamwork. These kind of projects you can never do alone, and you should hence learn to work together as a team. And this requires effort. Teamwork does not come for free, it is difficult. Another Similarity. You never have enough resources. You never have enough knowledge, enough time, and definitely you don't have enough money to do what you would really like to do. Supply chain complexity. The team, the car, which the team manager and his team will show you in a few minutes, is very complex. It has a lot, I think hundreds of parts, maybe even thousands of parts, which come from somewhere. They are made by someone, whether it's in-house or bought. This makes for a very complex supply chain. No difference than the big projects that we do. The systems engineering process. How do we know that what we are doing, we're doing well? We track this by an engineering process called systems engineering. There's not really a difference there. It's applied in all businesses alike. If you think, and this is also, by the way, for the live stream viewers, if you think that the technical reviews by alumni are difficult, wait until you have the technical reviews in a big multinational. They are, well, quite similar actually. And this is a good thing, because being sharp on the content makes your product better. So this is quite similar, and also you learn how to deal with positive critique, let's say. And last, but I think the most important one, I think in the team you learn that with just common sense, you know, what are we doing? Are we doing the right thing? Should we do something different? You learn to identify when to ask these questions. When should I stop and think, is what I'm doing the right thing or not? And when should you just continue and move forward? So use common sense. That's I think for all aspects in life, actually. Use common sense, that's generic. Now for the differences, Mickey.
Yes, but there are also some differences with working in a team and working in a company like Siemens. The first one is having experienced colleagues. I always say to everybody who wants to hear it, it's not what you know, it's who you know. And within Siemens, there's always someone with more experience and more education, sometimes even a lifetime of experience that you can ask questions and get right answers. As long as you know who to find, and there's always someone who knows someone. So that's the first lesson that I've learned within Siemens. Just go and talk to the right people, and they will point you to the right people, and they will point you to the right people until you find your answers. Very important one. The other one is that requirements of customers are not always clear, especially in these big infrastructure projects. The 100 million or even in more expensive projects, these are very, very tough projects with not always clear requirements. Steph mentioned one of the water cranes in the Netherlands, the sluices and the locks. You might say it has to go open and it has to close in a certain time. Well, that's just not it. There are many, many more requirements. It has to close in a certain way, with a certain speed. It cannot go too fast. It has to be automated. There are safety checks and so on. So even when a system seems quite simple and easy, some requirements are still hidden and not very clear. And it's our job to make sure that they are clear before we finish the project. The next one has a little bit of an overlap with the previous one, and that is that our most important customers are public customers. So we're talking about Rijkswaterstaat, ministries, the municipalities, provinces, and they have politics, and they have politicians, and they have a very important voice in the whole matter, and they have public, let's say, favor that they promise to all of us, and they have to fulfill them. And these are very important stakeholders because they made a promise to us, to everybody, and they have to make sure that they can keep them, and we are the ones that are fulfilling those promises. So they are very important people to talk to. And the last one is a bit of my favorite. In the team, we used to have saying, well, why are you doing something? And we always said, well, because I can, because it's possible. That's a bit difficult at Siemens. We have processes, we have guidelines, and yes, we can do some items just because we can and because it's possible, but it has to make some sense commercially, technically, safety-wise, and so on. But that's something that we have learned from the team within Siemens, and that's something we will keep learning. So the last slide, we promised that we would keep it short. I think we managed that. I think we have a record time this time. But all I want to say is that we are proud alumni. We are proud sponsors. And you might not know it, but all of you are sponsors as well, because you are the ones that made this happen for your family and friends. Thank you.
Hello? There we go. All right. Welcome, ladies and gentlemen, to the DUT17 design presentation. I'm very happy to see all of you here. I'm so happy that our engineers could bring their family, their friends, and to all the people that are following us in the live stream, welcome to you as well. Now, today, you will be shown the design of the DUT17, the latest in a series of Formula-style race cars that our Formula Student Team Delft engineers have produced. Well, they've designed it. The production is still ahead. I'll begin the presentation by telling you about Formula Student as a competition and continue by handing it over to Meerte Kroeze, our operations manager, who will tell you a little bit more about the team and what's gone on over the last 6 months for them. Afterwards, Jonas Holterman, our chief engineer, will tell you about our design and the design philosophy behind the DUT17. And then, Rogier Colijn, our technical manager, the man in charge of the finance and planning, is going to tell you what's going to happen afterwards. Where are we going after this design presentation? Before I begin, I would like to explain the difference between Formula Student Team Delft and DUT Racing. DUT Racing was our name 2 years ago. We are now Formula Student Team Delft. However, the cars are still called the DUT. DUT17 is the name of our car. We stuck to the name. It's a legacy. And that's a short explanation of why, but the reason is that we are actually more of a Formula student team than a racing team. And this has to do with the core principles of the Formula student competition. The Formula student competition is at heart an engineering design competition. It challenges students to come up with every element of a research and development project themselves. As you can see on the picture here, a student has to conceive, design, produce, assemble, and test the car. But that's not all. After a year of the project, they have to reevaluate their choices of last year and try to come up with a better design. Now, you can have a small conversation with the engineers in the room after the presentation, taking a look at the progression from the DUT14 to the 16 that are exhibited here today. The competition, however, is extremely large and produces a lot of cars. Here's a picture of one of the biggest events in Germany. It doesn't only produce a lot of cars, it also produces a lot of very qualified engineers. Now, a Formula student engineer is different to a regular engineer in the sense that he has learned for a year how to be more pragmatic about his design. How is he going to put his design into the world and make it actually work? That's something that our engineers have been taught through the Formula Student competition. I would like to explain the competition now to you through the eyes of our engineers at the competition by telling you about a week at a Formula Student competition. The competitions are a week long, and just to give you a little background, you have to get 1,000 points if you want to really have dominated everything. So everyone's trying to get the most out of 1,000 points. We begin by the arrival. The arrival is at a Formula One circuit. Anywhere around Europe or the rest of the world, these competitions are international. The students have probably seen this circuit many times on TV, watching Formula One. And they don't have much time to sit and look around because they have to set up the camp site. The tent is where they're going to be spending the next week. That's where they're going to be eating. That's where they're going to be getting the little sleep that they can. Here you see our engineers upon arrival trying to get the last hours of sleep while they can. They have a very tough week ahead of them. It's definitely a rough week. There are stories from the Formula Student Germany competition last year of our team manager last year banging pots and pans together, screaming, "Wakker worden, opstaan." They need all the sleep they can get. Now, after we arrive to the camp, the car is taken to the pits. At the pits, the car is set up and it serves as the hub of the team at the competition. Any small modification that has to happen to the car happens here. If another team wants to come and look at the design and ask questions and try to do some research for next year, this is where it happens. A lot of information is exchanged here. Now, at the competition, we're not allowed to have our high voltage systems on, and we're not allowed to use that stuff because it is a bit dangerous. So we have to push the car around. But what does that look like when we're moving the car from one competition spot to another? Well, it looks a bit like this. You see the car here being pushed around by one of our engineers, but you also see a large crowd of people following it around. They're all wearing team clothing, indicating they're teammates, and all of them have worked in some way or another on this car for the course of a year and have invested a ton into it. So they're very interested, and rightly so, in where it goes. Then we continue with the scrutineering. This is where the car will be allowed to compete in the competition. It's a series of different tests that it has to go through. There's an electrical scrutineering, there's a mechanical scrutineering, and there's also a series of tests that it has to go through. There's a rain test, there's a tilt test, and there's a brake test. Here you can see Daniel, our pilot from last year, waving from a 60-degree angle without the car rolling over. Hello, Daniel. Why do we do the scrutineering? Well, for good reason. Everything on the car is done by students, and the safety systems are also by students. So it's very important that we get it right and that nothing bad happens at the competition, because we're also putting a student into the car, no professional driver. Then the engineer will take a look at the static events. The static events are the place where your car gets judged, but not the actual performance of the car, the choices that went into getting to that car. The first one is the business plan presentation. Here you see Vincent and Leonard, our guys from last year, getting ready to go and present. They have to basically sell the car to a jury that role plays as a series of investors, and they have to make the case that their car is the best. Afterwards, the engineering design event. Engineering design, the engineer has to go and explain to everyone exactly why the choices were made from a technical standpoint. This is very difficult sometimes, but it's also the place where they can really understand, hey, why is the car built the way it is? It's the place where the choices are really evaluated and the trade-offs are really examined by the judges. They also get the design a few weeks in advance, so they can kind of cheat a little bit that way. And finally, the cost report. The cost report is where the skill of the team in categorizing everything that goes onto the car is measured. Not just that, also the processes that every part goes through before going onto the car have to be measured in a financial way. Here, accuracy is very rewarded. This finishes off the static events and brings us to the dynamic events for the evening. The dynamic events are a series of 4 events which have 5 different ways of scoring. Now, I could tell you about them, or I can quickly show you a video, beginning with a skid pad, which, well, very impressive.
Here goes the electric car right here that's really fast. See, there's lots of different ways they can mount it. So, here goes this electric car.
Delft is lining up for their third run.
This is the fastest. Looks like it's on the rails.
It sounds like a high-speed train.
It looks like a clean run from here.
So you may have heard the woman in the audience on the video saying, it looks like a high-speed train. Indeed, it looks like it's on rails. In the next event, the acceleration, very simple, go fast in a straight line. I'll show you a video. Yeah, we're talking about a car here that does 0 to 100 in about 2 seconds, just over. The next event, the autocross. This is, in my opinion, the most exciting one. It's the one where the driver skill gets tested the most. And yeah, you basically have to do a lap of around 1 kilometer. And, well, I'll just show you. Concentration that the driver has to have in such a situation is intense. Have you seen how close those cones are together? Well, in the next event, the endurance and efficiency, the driver has to do 10 of those laps in a row. So, yeah, he does do it a slightly little bit slower, but that's because it's a very long race, and it's also judged on the efficiency of the race. Hence, the endurance and efficiency event. This is also a part where a team can play a little bit of strategy. It's in their interest to get points from endurance by racing quickly, but at the same time not too quickly because they have to win points for efficiency as well. The event ends after all these different competitions, but a lot of stuff goes into it before to make it all happen. And that's why we have an operations department in our team to organize the logistics of the event, do the management or the marketing, and kind of like a superhero to the team. They also have organized events like today, and I would like you to give them a round of applause for the great work they're doing today. They're also managing the cameras right now. So thank you, Operations Department. And I'll leave you with a video from our media partners' workflow that they took of us at the competitions last year that touches on most of the elements that I talked about today, and leave you with Meerte.
So, thank you very much Workflow for making this amazing video of the Formula Student Germany competition. My name is Meerte. I'm the operations manager from the DUT17 team, and I will be talking about the past few months, how we've got here, and how this awesome team got to this point to actually being a team. So you see a kind of messy team photo, so the actual team is not that messy. We added a little bit of structure. So in the top you can see our management, the official management positions. So as the team manager, the chief engineer, the operations manager, myself, and then the technical and finance manager. And because we have a management structure, in that way we can make proper decisions and everybody knows what is going on. When you have a problem, you know exactly who to turn to and who you can talk to. And that makes a lot of things very clear for all the chiefs. And you can see all the chiefs in the bottom. But before you can make an actual team, you have to know some background of all the people you're going to be working with. That's why I added a little bit of statistics. These are all the faculties our students attend. So you see the largest group, the blue group, those are aerospace engineering students. We have a lot of aerospace engineering students with us, but a large and steadily growing group are electrical engineers, which is kind of the thing you want to go for if you build an electrical race car. What you can see as well is that we have a lot of different faculties, but we are actually missing one faculty, and that is architecture. So if there are any architecture students watching right now, join us for next year. So another interesting fact that we have is the nationalities. We have 21 different nationalities in our team. The biggest part is still Dutch, but we are a Dutch team, so it kind of makes sense. But one of my favorite numbers is actually the male to female ratio. I'm kind of afraid to show you because we have 71 guys and 2 girls. Yes, so maybe for next year, recruitment committee, please more girls in the team because we're awesome. But let's stop talking numbers because you don't need actual numbers, you need people to make a team. And that's why we recruit. We go to faculties, we stand there with a car, we stand there with previous team members, and just talk to people like, hey, would you like to join our team? What we also do, we have interest drinks, and people even send open applications to our operations email to ask, hey, can I join your team next year? So after recruiting, you get an interview, and after mutual acceptance, you get invited into our team, into our family, and then we have a kickoff. And in this kickoff, we really set the expectations of the core team that we set for our team and that we set for our engineers. And we really make sure that the expectations are clear to all the engineers. And after the after all these I will just continue. We will just have a rules test. Okay, we have a rules test. And we have our design limits, we have our safety, because safety is very important, because you don't want your wheel flying off, like Pietro already showed you. But Jonas, our chief engineer, will tell you much more about the rules and the implementation of the rules. So the team really needs to work together on building a car and not building separate departments and not building separate parts that we will put together after our design and after our production phase. So if you really want to build a team, you have to do some team bonding. So let's start building a car. This is the top-level packaging exercise. This exercise is to generally know where you want to put certain parts of your car. If those parts don't fit in your car, your car can't drive. That's why it's kind of important to do this exercise. Some people went a little bit overboard with enthusiastic new ideas, and that resulted in some good laughs as well. But laughing is part of team bonding. And after the first phase, we went on our team weekend. As you can see, some rivalry, some competition, some team building exercises, and just getting to know each other better, because you will be working a full year with each other. And that will also mean you have to know each other, you have to know if you can trust in each other, if you can rely on one another, both in a personal and in a professional manner. So we ask our engineers as well if they want to sit in with their reviews. The engineers sit together with alumni, with partners, and also with the other engineers to get constructive, but most of the time also a little bit feared feedback, because the alumni have already designed and built a car, so they know a lot about what you're trying to do. And that is sometimes quite impressive, but also a little bit feared. These reviews tend to take quite long. I think normally they take up until 3 o'clock in the morning, sometimes 2 o'clock in the morning, so late and short nights. The engineers spend a lot of time in the office, almost 24/7 there are people in the office working hard on finishing their design. And our final design phase has just ended before the Christmas holiday. And to make sure that it's a little bit bearable and that the enthusiasm is still going on, we luckily have our team manager, who was bringing gehaktballen in the middle of the night through the dream home. So we had our big events. Now just take a step back and look at what we do in a day-to-day basis as a DUT17 engineer. So we have our live at ad hoc. We try to spend our time as efficient as possible, so we have more time to work on the actual car. So we have some handy tools. We have a cooking schedule where engineers get lunch. 2 engineers get lunch every day, and 3 engineers cook dinner every day. Every day. And by eating together, it means team bonding. You get to know one another better. You can laugh and talk to each other about the fact that we eat pasta rood so many times a week, because it's very easy to make. And we really try to avoid hungry engineers, because I can tell from experience, a hungry engineer is a grumpy engineer, and a grumpy engineer is a bad engineer. So we really want to avoid hungry engineers. That's why we have Meert's Winkel. That's my little shop. We have all kinds of snacks provided for our engineers. We have some chips, we have some sugar, and we buy it using the left computer. That's the bliepgeit. So you use the scanner, you scan it, and all the things you buy and eat are put in your account, and then the finance manager will take the money from your account. On the right, you can see our countdown Jetser, all the biggest events, the important dates, birthdays, but also very important holidays are shown in this computer, because we even spend holidays together. As you can see on the left, Sinterklaas came to visit us. Unfortunately, our engineers were working so hard on the detailed design that they didn't have time to go to Sinterklaas. So Sinterklaas came to visit us in the office. And on the right, you can see our very real Christmas tree. You may be able to see that DUT17 engineers decorated the tree, because next to some balls, there are parts of cars in the car. And at the very top, you see our 3D printed chassis. So now I will continue to the most frequently asked question, like in competitions, but also on our email. How do we get such good drivers, and where do we get them? We get them from our team. To quote the DUT17 team manager, the car you build is only as good as your driver, which means a faster driver is a faster car. So we go on kart outings 3 times a year to get to know each other, to get some rivalry between the departments, but also mainly for the driver selection. Because if you drive very consistently through all these events, you get into driver selection. This will mean you will be trained as a driver. That means you will be grilled by one of our chiefs into working out. But it also means driving in previous cars, and the thing you really want as a driver is to drive in the DUT17, of course. So now you know almost everything about the competitions and almost everything about our team. I will wait for the moment you've all been waiting for. The actual design of the DUT17. So I would say, buckle up and enjoy the ride.
Wow. What an amazing car. Ladies and gentlemen, welcome. I'm Jonas Holterman. I'm the chief engineer that is responsible for this marvelous machine. And you've just seen what we've been working on so tirelessly for the last 4 months. Now, while I'm here, I want to talk about more why what you just saw looks the way it looks. I'm going to touch upon a few of the details that really make the DUT17 something very unique. Now, just like our design process, I want to start by what I would refer to as the Formula Student Scripture. That are these 120 pages worth of rules. And they govern pretty much everything about the car. Now, to really highlight what these rules actually mean for us, we started out by compiling a list of parts that are affected by these rules. And somewhere around the middle, we stopped and thought, hey, let's do it the other way around. Let's make a list with parts that are not affected by the rules. And that ended up being a very short process because we found out that basically the shape of the brake disc is pretty much the only thing that is not governed. So instead, we made that short list. Now, the rules not only govern parts, they also govern the entire competition that you've just heard about from Pietro and Myrte. And after a few rules changes this year, the FSG rules that I have here in front of me are the rules that we're designing for. They form the entire basis for our design, and this is where we also started with our requirements. Now, from the dynamic events, the acceleration, skid pad, autocross, endurance, and efficiency, we boiled it down to 3 main things that we want the DUT17 to do. We want our car to have high accelerations. Now, what does that mean? We want it to go very fast, very quickly forwards. That means accelerating quickly, braking quickly to decelerate backwards. We want it to turn into corners very quickly, and we also want it to be very fast during a corner. The next pillar on here is efficiency. We want to score as many points as we can during the efficiency event. That means with more efficiency, we can have a lighter accumulator, we can have a lighter car, we can have a faster car. And the last one on here is reliability. Pietro told you about the endurance, that's 22 kilometers in total, and the car has to run for that entire time. Now, while the rules are very strict on most things, they also allow us a great deal of freedom to achieve these requirements. But there was so much freedom with just 3 words that we thought 3 words just isn't enough to describe the entire car, so we expanded it to, well, 6. These are our own requirements added in, and I want to start by talking about the way we handle the car. We not only design it, we also build it, we test it, and we use it at the competitions, which pretty much means that things will break. So we design the car to be as maintainable as possible, so that at the middle of the night you don't have to tear the entire car apart to reach that one bolt in the middle that you have to undo in order to remove one section. The next one is about the way the car is driven. We test it after we've built it, we use it at the competitions, and even the year that comes after us will be interested in using the car for their own tests for their control systems, for instance. Overall, that's about 2,500 kilometers that the car will have to be able to drive, and that's why longevity is on this list. Now, we've designed a marvelous machine here, but at the end of the day, we have to stick a human into it, and that human has to be able to drive it well, and that's why drivability is on the slides here as well. Next up, I want to skip to the systems and subsystems that really fulfill these requirements. Now, saying 6 words and saying that's the car you want to build is quite easy. Coming up with the things that are actually going to do this is a little bit more difficult. I can't do that job by myself, and that's why we have departments. Now, each department covers one facet of the design, and since facet is a very small word, I try to sum up every department with one word. Vehicle dynamics, the first one, is theoretical. Chassis is structural. Suspension is geometrical. Drivetrain is rotational. Powertrain is electrical. Electronics is integrational. Aerodynamics is essential. And controls is magical. Now, I want to dive a little bit deeper into each of these departments to really explain what it's all about and build up the car in a logical fashion. We're going to start with the department that has the least number of parts on the car, but actually has the most connections with every other department at the same time, and that is vehicle dynamics. Now, vehicle dynamics designs where the rubber meets the road. They are responsible for our signature 14.5-inch tires, and the DUT17 has a new iterations of these tires coming. Unfortunately, I can't really tell you what's inside. That is top secret. Next to the tires, they are also the only department that really knows what the car drives before we build it. That means they have to do a lot of modeling, and that's why I brought one of our earliest analyses here. This is the results from quite a simple model of the car driving on a virtual track, and you can actually see the speed here that it can take during the corners. This is one of the simpler models. We also have more advanced models. For example, the steering effort, the amount of force that the driver needs in order to turn the steering wheel. And that ultimately comes back to drivability and how hard we have to train our drivers during driver training, like Myrte told you. Now we've talked about the department that sits above the car. Let's move on to the department that really sits at the center of the car, the chassis department. Now, some of you may expect me now to introduce the chassis with bread and cheese and ham as a sandwich structure, but there's actually much more to chassis than that. Most of the time, with a few exceptions, the chassis department actually works quite hard at improving the ergonomics. Again, back to drivability. It also has to accommodate all of the other departments inside and around it. For example, all the motor controllers have to fit inside, the accumulator has to fit inside, the driver has to fit inside in the first place. And last but not least, the crash structure underneath the nose of the car is also accommodated in the event of a frontal impact. What I haven't mentioned yet is the biggest interface of chassis on the outside, and that's the suspension department. Now, suspension designs between a rock and a hard place, they have to attach the wheels to the chassis. In our case, though, they also have to attach the wings to not the chassis, but the wheels, actually. I'll talk about that a little bit later. The bread and butter of the suspension department are strong carbon rods. And while they can take a lot of force, there's actually something much more impressive happening with the DUT17 suspension. And that concerns the blue and red assembly that you can see in the render here. And this is our spring damper system. We call it the SDS. Some of you may know it as shocks. It's the red and blue thing. Now, our SDS is active. What does that mean? That means in each of the 4 spring dampers that we will have on the car, there are 2 tiny mechanical valves that will be adjustable by the control systems of the car while it is driving. What does this do? This enables us to really control the motions of the chassis while the car is driving. If you imagine you're braking, you can hopefully tell that in your car that you just came here with, it goes a little bit forward. We don't really want that. And the same goes for accelerating, the car going backwards, and in corners, the car will also lean to the outside of the turn. With this, we can control that. Now, back to that wing attachment I mentioned a second ago. As you walked in, I saw many of you taking a look at the cars that we had on exhibition here. And if you took a close look at the DUT17 behind you, you may have already seen the predecessor of this system. We call that our floating front wing. Now, this attaches the front wing not to the chassis, but directly to the wheels. That means that the aerodynamic downforce that the front wing generates does not have to go through the chassis, through the spring dampers that we just talked about, to the wheels, but directly to the wheels. Much simpler, right? It also means that the ground clearance of the front wing is a little bit less of a problem, so we don't have to worry about quite as much it hitting the ground while we drive. We also have a very similar system for the rear wing. Now, the rear wing is about 1 meter off the ground, so we don't really care about ground clearance in this case, but we really care about the high downforce that it generates being directly transferred to the wheels. Now, with the suspension department, we've just attached the tires to the chassis, but we haven't really talked about what goes inside of the tires, and that is drivetrain. Now, drivetrain is really governed by one mission, and that's transmission. Here you can see our transmission and how the rotation of the motor in the smaller gear in the center is transferred to the tires on the outside with the big gear. Now, the 3 center gears remain stationary, and because the big ring gear is orbiting around the center, which is called the sun. This is called a planetary gear set. Now, we've used this a few times in the past already, but the one thing that we really learned by using this is that the most important thing about making use of this design is to properly attach your ring gear to the rest of the tires. And that's why these little nubbins that you can see on the render are in there this year. But there's also more to drivetrain than just a few gears. This is our entire inner wheel assembly. And if I may walk you through it, on the left you have the tire, then comes the motor, the wheel hub, the upright to keep everything upright, the transmission, and on the very right we have the brake and its caliper. Now, we've talked a lot about spinning gears, but what actually spins the gears? It's the powertrain department. Now, like a train, you have to start somewhere, and I'll start at the beginning. At the beginning of powertrain is the accumulator. This is our accumulator from the inside, and you can see quite a few high voltage wires, the black wires in this case, and a lot of PCBs. These are our sensing boards that sit on top of the accumulator cells and are mostly responsible for the safety of the entire system. As you also may be able to tell, this looks quite compartmentalized. And this is for reasons that are specified in, you guessed it, the rules. These are 2 of these compartments, and inside each of these modules, we have 24 of these. This is a model of one of our accumulator cells, and having them in 24 separate packs boils back to one of our requirements that I talked about earlier, and that's maintainability. Being able to take these apart with the accumulator open and then having separate smaller blocks means it's a lot easier and, more importantly, safer to work on. Now, 24 cells in one module means that we have 288 cells in the entire accumulator. Each one of these cells weighs about 120 grams, and that makes the accumulator the second heaviest part in the car, apart from the driver itself. And that means that you want to design each part within the accumulator as lightweight as possible to make that second heaviest part as lightweight as possible. Now let's move onwards in the train to the motor controllers. We have 4 motor controllers because we have 4 motors. 1 motor in each wheel means that in total we have a greater than 1-to-1 ratio of horsepower to kilograms of vehicle weight. And that's something that's very mystical in the car world, and that's something that we're very proud of. So here it is. We have a rolling chassis with motors inside, a fancy drivetrain, and good suspension. Now, this is not the entire assembly, of course, but at this point I will hand over to Rogier, our technical manager.
Hello. Thank you, Jonas. So, up to this point, we have built quite a nice car, but there are still three very important departments missing. The first department I will introduce is a department with a little bit of an image issue. I will go to the next slide, and you will see a change. But as you see, it's quite a small change. Not much changed on the car. But this department is actually very important, and this is the electronics department. I will make the chassis a little bit of transparent, and then you can see that the electronics department is actually everywhere in the car. The electronics department basically takes care of making sure the entire car drives. Now, how do they do this? First of all, there's the accumulator, which Jonas just mentioned. But the accumulator is basically a beast with a lot of power in it, and this needs to be controlled. This is done by the accumulator management system. This system ensures that the power flows safely throughout the car and makes sure that all the systems do not light on fire, basically. This is basically the heart of the car, you could call it. The next part of electronics is the wiring. The wiring not only transmits all this power throughout the car, but it also transmits all of the signals from the sensors throughout the car. This wiring is very important and can kind of be seen as the nervous system of the vehicle. Lastly, there is the ECU, the electronic computational unit. And this takes part of running the software on the car, which really gives the car the performance it needs. Now, talking about that software is very important for us. Here, you see a mock-up of our new dashboard this year. As Jonas mentioned before, drivability is a very important factor in our car design, and giving the driver the input he needs is very important. And that is why this year, we are completely redesigning our dashboard. With this dashboard, the driver gets more information, for example, about when he is regeneratively braking or mechanically braking, which allows him to fulfill the 22-kilometer endurance event. The controls and software department not only does this, but they also write the vehicle dynamics controller. This is the controller that individually controls the 4 motors on our car and makes sure that we get the cornering performance we need. Now, talking about cornering performance, the next department I'm going to be mentioning is very important when it comes to this. This department basically has 2 jobs. First of all, it gives us enough downforce for the car to go to the corners as fast as it can. But second of all, it just makes it look really cool. And that is the aerodynamics department. And with this department, the car finally looks like a finished product. Now let's take a step back and see what the aerodynamics department does. You've all seen the classic example of an airplane flying and its wings producing lift. Now what do? Take this airplane, flip it upside down, stick some wheels on it, and drive it on the road. Now, in order to illustrate how important the aerodynamics department is to our team, I have a little video that shows you Kimi Räikkönen in 2004 losing just one of his rear wing elements.
So hard. Here it is again. Look at this. Wallop!
Oh, there'll be some grimaces back at the McLaren factory. No retardation. Here's another angle of it, and boom, off it goes. And well, nobody is more surprised than you when you're driving.
So hard. Here it is again. Look at this.
So basically, he loses a single element of his wing, and the entire car falls apart. It's no longer able to get the cornering performance that the engineers calculated for it. And that is why we have designed the DUT17 aerodynamics package, which you can see behind me. Now, what is special about this aerodynamics package? Well, first of all, it looks really nice, but one of the new features we have added to this year's package is a 2-element DRS system. Now, for everybody that is not aware, a DRS system stands for drag reduction system, which basically reduces the drag of the car when required. Standard cars have a single element DRS system where one of the elements flips open and basically reduces the drag on the car. This reduces the drag by about 30%. Now, what we do, we also flip the second element. And this allows us to have another 10% extra drag reduction to give us more acceleration on the straights during the autocross event. And this, hopefully, will lead to faster times during the competition season. So now that you've seen the entire design of the car, let's take a little step back and have a look at how we got here. How did we make this car? Well, we did this with design monitoring. Basically, as Mirtz already mentioned, our design was separated into 4 phases. First of all, we started off with the research and analysis phase. Now, as many parents in the room know, your child probably signed up for the team this year, and they had no clue what they were getting themselves into. They might know something about cars, but the part that they were assigned is very new to them. And that is why during the research and analysis phase, our engineers have a look at what has been done before, what are the requirements for their part, and very importantly, what do the rules have to say about their part? Because at the end of the day, we do want a car that is rules compliant. Next, the engineers get to some actual designing, and this is what they do during the conceptual design phase. They start drafting concepts, sometimes goofy concepts, sometimes nice concepts, and at the end of the conceptual design review, design phase, these concepts are traded off, and the engineers enter the next phase, the preliminary design review. At the end of the preliminary design review, we basically have a rough idea of what the car is going to look like, but it's just not quite there yet, and that is why we have the detailed design review. The detailed design review is really the bulk of most of the work, and this is where literally every bolt, nut, and washer gets put into the car design and ends up with the car that you have just seen. Now, at the end of all these design reviews, at the end of all these design phases, we have reviews. These reviews are a vital part of the way we design the car. Behind me, you see a graph of the design mistake implication over time. So if a mistake is made, what happens if this mistake goes unnoticed for a long time? Basically, it goes out of control. At the end of the time, you have a very large mistake in your car that might make it not rules compliant or not perform the way you want it to. And that is why with these design reviews, we are able to mitigate the impact of these mistakes, and at the end, we have the awesome design that we're all looking for. What do these design reviews look like? It's basically some engineers, we put them into a room, we put some alumni into the same room, and we have them look at each other's designs and give criticism. This criticism is scribbled down, and then over the next weeks, the engineers will take this criticism and make their car even better, make their part even better. Now, at the end of these reviews, and at the end of the detailed design phase, you have a car. Now, if this were a standard university project, you would write a nice report out it. Given the car we built, we would probably get a pretty nice grade for it, and we would be done with it. But that's actually where Formula Student is completely different. We actually start building the car by moving into the production and assembly phase. And this is where we will need a lot of help from all our supporters and sponsors. And an old team manager always used to say that parents are the biggest sponsors because they give us the engineers, so thank you. The production and assembly phase is basically the phase that we are entering right now, at this very moment. Our engineers can do a lot of the work themselves. Behind me, you see this year's chief chassis working on last year's chassis and making sure that it is awesome the way it is. Please notice his work in the rear left of the room. But we can't do everything ourselves, and that is why we have our sponsors. For example, this is one of the chassis molds that were being made only a week ago at Airborne right here. After the production phase is over, we move into the assembly phase. We basically have all the parts laying around in the workshop, and we put them together. This is actually really, really difficult, and this is where the engineers have to really dive back into their design and see, how are all these parts supposed to be together? And at the end of the assembly phase, we hopefully have a driving car, which we will reveal at the city center in Delft, hopefully somewhere end of May, early June. Now with this, I would like to conclude the presentation, and I would like to ask my co-hosts back on stage with me. And we are now going to be taking a group picture, because this is one of the few moments that we can actually get this many people of the team together. So I would like to ask, first of all, the Aerodynamics department to come on stage with us.
Hang on a minute. We've briefed the team slightly differently on this. So in order to keep things civil, I'm going to briefly explain what's going to happen. We want to give everyone credit for the work that they've done, but we also don't want to make this a complete mess. So we're going to call up the departments. They're going to take place on either side of us, and then at the very end, we take the positions that we know, take the team picture, and then we're going to end this here. So let's start with aerodynamics. Go over there.
The next department is the chassis department.
Next up, Powertrain.
I would now like to ask the electronics department to come up to the stage.
Then we have vehicle dynamics.
Will the controls and software department please enter my side of the stage?
Then we have suspension and drivetrain. Yeah.
And then there is only one department left. A really important department on a day like this, which is of course the operations department, who has set most of this up.
Now this is the point where we're going to say goodbye, hopefully, to the internet. And I would like to extend my thanks to all the people that made this day happen. Thank you very much to Siemens. Thank you very much to you guys from Workflow. And thank you very much to you guys, the parents that made our engineers, our team possible. Thank you. Yep. Team! 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 Okay, and now we have drinks and snacks for everyone right over there. You're more than welcome to take a look at the cars as well, and have a good night.